is we're going to take those rules of logs we used, right, and start to apply them to some problems. These, maybe not so much. You might decide to apply the rules or not. We'll see. The first question says the log of 1. Think of the question you're being asked. It's saying, what power do you put on 10 to get 1? Your answer should be 0. Okay. Here are the second two problems. If you look at these two questions here, this one and this one, I claim they're really the same thing. So hopefully you noticed that. So I guess you could pick whichever one you want to answer first. Right? If we look at the first one, this is saying, hey, what power do you put on 10 to get 0.01 or 1/100th? Well, you might remember scientific notation, right? Where if you take 10 and you move the decimal back a couple, not 10, but 1, move the decimal back a couple of places, you get 0.01 or -2. Okay, and that's because 10 to the -2 power is 0.01. That's one way to remember it. The other way is to take the second example. When I look at this, I could think of this as the following. I could think of it as 10 to the, well, I'll think of it two ways. I'll think of it as 1/10 squared. And that looks promising to me. I'm always happy when I see 10 to a power, and I'm taking the log of it. All right? The only problem is it's in the denominator. I don't want that 10 in the denominator, so I'm going to rewrite this as log of 10 to the -2 power. And then that's really just a silly question, isn't it? Right? 10 to the -2 power, saying what power do I put on 10 to get 10 to the -2 power? Sounds like you're talking in circles, which you are. You get -2 for an answer. Okay. Now, I'd like to take advantage of answering silly questions. So I'd like to make this look like 10 to a power. And I could do that actually pretty quickly. I can say that instead of saying 10 log of square root of 10, I could say log of 10 to the 1/2 power. Because the 1/2 power means the same thing as square root. Well, now this is a silly question. It's saying, what power do I put on a 10 to get 10 to the 1/2? Well, the answer to that is just 1/2. Okay. And then if we go up here, this question in my mind, it's the same idea. It's saying, what power do you put on 10 to get 10 to the 3rd is 3. Okay. This next problem, this is a slightly more fancy version of that question, a little subtle trick. I see the square root of 10. The only problem is that square root of 10 is in the denominator, so you should rewrite it this way. Log of 10 to the -1/2 power. And then it's a silly question again. What power do I put on 10 to get 10 to the -1/2? -1/2. So far, so good. These last three questions you can answer two ways, especially because they have nice exponents. And here's what I mean by that. Log of 100 is just 2. So this is really saying the same thing as 10 to the 2nd power. And the answer is 100. Okay. Look at the next example. Log of 1. Well, log of 1 is saying what power do I put on 10 to get 1? We know that's 0. So then I'm doing 10 to the 0 power. Well, that's just 1. Okay. And then lastly, this exponent is asking me log of 0.01, or what power do I put on 10 to get 0.01? Now I know from the second example that answer would be -2. So it's 10 to the -2 power. But 10 to the -2 power is 1/10 squared, or 1/100, which is 0.01. Now, I said that there were two ways you could have done these questions. That's probably the way most of you would try to do them. Okay? But I want you to notice something. Notice how all those numbers are the same. Now, my claim is you should not be surprised by this. All right? Let's think about what log 100 means. When we write log 100, that's equal to the power we put on 10 to get 100. Now, you happen to know in this case that that number should be 2. That 2 is the perfect power to put on 10 to get 100. But even if you didn't know that, if for some reason you didn't know what log 100 was, you didn't know the answer was 2, but you knew what this sentence was telling you, you should still be able to answer the question. Log 100 equals the power we put on 10 to get 100. Well, I'm taking 10 to the special power we put on 10 to get 100. By definition, you have to get 100. All right, so why is this sort of interesting to think about? Well, some of you could just say, well, I'm going to ignore what you just said because I know what log 100 is. It's 2. And I know how to do 10 squared and get 100. So I don't really need to know that. Well, I can change things pretty quickly for you. I could just say, hey, what about 10 to the log of 117? Uh-oh. And I'll say this. I'm willing to bet most people, right, do not know what the log of 117 equals. Okay, it's some kind of decimal, slightly bigger than 2, but we're not quite sure yet. Let's think about that exponent. This exponent, by definition, is equal to the power we put on 10 to get 117. And I don't know what that number is, and it doesn't matter. I know it's the special number that will achieve that goal. If I put it on 10, I should get 117. Well, this question is saying, hey, put that number on 10 as an exponent. So by definition, you have to get an answer of 117. Okay? So now we have a second rule, because we talked yesterday about this. We said if we had log of 10 to the triangle power, we said that was just a silly question, right? It was saying, what power do you put on 10 to get 10 to the triangle? Well, the answer just has to be triangle. Now, we just learned a moment ago was that if we take 10 to the log of triangle power, that should also be triangle. Log triangle up here means what power do we put on 10 to get triangle? I'm putting 10 to that power, I have to get triangle. So you might be tempted to say, well, look, this thing on the left equals triangle. This thing on the right equals triangle. So these two things must be equal. So let's write that down. Oh, those must be equal. So log of 10 to the triangle has to equal 10 of log to the triangle. And my claim is, yeah, that's good reasoning. They both equal triangles, so they have to equal each other. However, these two things are really not quite the same. And here's the reason. My claim is, if we look at the expression on the left, there's numbers you can plug in for triangle that you could not plug into the expression on the right. Let me say that again. There are numbers you can plug in for triangle on the left that you could not plug in for triangle on the right. So we need to remember that we can't take the log of 0 or something negative, which means that this exponent here, I'm only allowed to plug in things for triangle that are greater than 0. Now, you should ask yourself, is the same thing true over here? Right? Can I only plug in positive values for triangle? The answer is no. We've seen in the previous example, right? We saw things like, hey, here you go, 10 to the 1/2. Well, that's greater than 0. But then we also had over here 10 to the negative 1/2. Look at this example, right? So we were allowed to plug negative numbers in for triangle, as I called it. So here, in this case, triangle can be any real number. Okay? So that's the difference between these things. So yeah, they're equal, but only when triangle is greater than 0. Because when triangle is greater than 0, both of them have an answer. But the thing on the right would not have an answer when triangle was equal to 0 or less than 0. Okay? I'd like to introduce to a very special kind of log. Sometimes you'll see this, ln of x. And you might have seen this in the past, and you got nervous when you saw it. You thought it was something different. That's right. This is really just log base e of x. That's all this is. It's saying now my base is e. Turns out to be a very handy thing. Helps you out with a lot of problems that you try and solve in calculus. Let's go through a set of problems then, having to do with that utilize ln. So for example, let's talk about the ln of 1. The question is almost the same. What power do we put on e to get 1? The answer is 0. Okay, let's try a few more. How about this one? ln of e to the 0. ln of e to the 5th. ln of square root of e to the ln 2, and ln of 1 over rad e. So the second one's kind of silly. I mean, if you think about it, e to the 0 is 1, right? So it's really the same thing as the first question. But I claim it's even easier to tell that the answer to this is 0, because this is just a silly question. Because ln is saying, what power do you put on e, right? And we're saying, what power do you put on e to get e to the 0? Well, the answer has to be 0. What power do you have to put on e to get e to the 5th? 5. Okay? A little bit of thinking in this problem up here. What power do you have to put on e to get square root of e? Is really saying, what power do you put on e to get e to the 1/2 power? Well, that's 1/2. Okay, let's skip down to this one here first. Let's think of that as the ln of e to the negative 1/2. And once you do that, it's another silly question. What power do you put on e to get e to the negative 1/2? Well, negative 1/2. All right. Now, this question. That's a special one, right? The question is, what does ln2 mean? So it's the power you put on e to get 2. That's what the meaning of ln is. Now, I'm willing to bet that probably no one really knows what that number is. But I'm putting it on e, so I better get 2 for an answer, by definition. All right? So now I actually have 2 more rules, 2 more of the triangle rules, as I call them. I know that if I have the ln of e to the triangle, I should just get triangle. And I also know that if I have e to the ln of triangle, I should just get triangle. All right? Now, again, with the same restrictions. Over here, triangle has to be greater than 0. But here, triangle can be anywhere. It could be all reals, all real numbers. Okay? So that's how we write it. So let's look at a few more. Some problems that are surprising that you can get the answers of. Let's take a look at this one. How about the log of 10? Or how about this? The square root of log 100 minus the log of square root 100. That's sort of an interesting question to think about the order of operations, right? And the second problem, what's different about the first term and the second term? How about this? Log of the square root of 10 times the 4th root of 10 times the 5th root of 10. Okay? And then here's a fun little challenge. This one's not as easy as those. Oh, let's do these 3 first, and then we'll get to that next one. Okay, so for this first one, you just have to do the inner log first. Well, the log of 10 is just 1 because it's saying, what power do you put on 10 to get 10? So this turns into the log of 1. But that's saying, what power do you put on 10 to get 1? So the answer is 0. It's not so bad. Okay, as I was saying earlier, you have to worry about order of operations. In the first expression here, I'm asking you to take the log of 100 first. Well, we know that's going to be 2. So this becomes the square root of 2. Okay? In the second example, we're taking the square root of 100 first. So this becomes minus the log of 10. Because the square root of 100 is 10. We know that that's going to be 1. So we get the answer square root of 2 minus 1. Okay. Now, this last question, I'd like to simplify it a little bit. But the problem is this doesn't look like the rule that I love so much. I have 2 rules that I love. Here's one of them. Log of 10 to the triangle power is just triangle. I would love it if it looked that way, and it doesn't. But we can get it to work out if we just do a little bit of thinking. Let's think of this as the log of 10 to the 1/2 times 10 to the 1/4 times 10 to the 1/5. And actually, this looks a lot more promising now. Because I know if I have the same base and I'm multiplying, I could just add the exponents. So this really becomes the log of 10 to the 1/2 plus 1/4 plus 1/5. Okay? Which, according to the triangle rule, the silly question, this is really saying, what power do I put on 10 to get 10 to 1/2 plus 1/4 plus 1/5? Well, the answer just has to be 1/2 plus 1/4 plus 1/5. Here comes the hardest part of the question. You have to add fractions, which nobody likes, because you have to get common denominators and things like that. Well, I'm going to think of this as 2/4 plus 1/4 plus 1/5. So that's going to be 3/4 plus 1/5. Common denominator would be 20 now. So this is going to be 15 over 20 plus 4 over 20, or 19 over 20. And there you go.